Hello and good morning, class. Let's quickly start with our lecture. I will start from the point where we stopped yesterday. We were talking about the thick cylinder, and initially we were discussing the differences between the two types of cylinders. And now we are going to derive some correlations for the calculation of radial stresses, hoop stresses, and the longitudinal stresses. So, for that, this person that is Gabriel Lamb proposed one theory, and obviously every such kind of theory or derivation process do need some kind of assumption, and the purpose of these assumption is to make things convenient and workable for all the stakeholders. So for this one, it was assumed initially that the material is homogeneous and isotropic. Now, what does this statement means? That whatever is the cylinder, it has the same modulus of elasticity, this Poisson's ratio, because these are the material properties, and it has been assumed that the cylinder for which these calculations are valid are does have the same material throughout its entire length or cross section. And the second assumption that has been made is that the plane section perpendicular to the longitudinal axis of the cylinder remains plane after the application of internal pressure. Now, which one is the plane cylinder? Now, if this is the cylindrical body, and if I cut a cross section over, I will just show it over. There is no figure over here. Okay, so let's suppose this is our cylindrical element, and these are the longitudinal stresses which are acting over this cylindrical cross section. Now, due to these stresses, it tends to elongate, but it says that the plane section after the application of will remain plane. Now, it says that there won't be any permanent deformation in this longitudinal stresses. So, why there won't be any permanent strain in this cylinder is that because it has assumed that this strain which is acting on the cylinder is same at all the points. So whether I take the longitudinal stress at this point or at this point or at this point, it will remain same and it won't vary with respect to the thickness or the radius of the cylinder. And the third property is quite simple, that the fibers of the materials are free to expand or contract independently with respect. So each fiber, for example, in the case of beams, we tend to see that there are different layers. So it says that if there are such kind of layers, then each layer has the tendency to contract or expand independently, and it does not have to take the impact of other layers. Now, these first two assumptions will be used in the derivation that is to follow, and I will show you where we have used this concept to make our work quite simple. So, let's move on to the derivation part. Can you see the whiteboard?
No, sir.
So, I believe, hmm, I believe not.
Yes, sir.
So,
Yes, sir.
before moving on to the derivation, it is important to understand these figures. Now, let's assume that this is the cross section of a cylindrical element, and this is a thick cylinder. Now, since we have this cylinder, and there are certain terms that we need to understand. First, obviously, that there is some kind of fluid that is present inside the cylinder, and this fluid is pressing onto this cylinder or inserting the pressure, which is being denoted by this term PI. And then the second thing is that it has been deduced that there is some kind of external forces that are also acting on the cylinder. So you can imagine that this is a confined cylinder, and due to the external soil maybe that is present around it, it is also exerting some pressure, and that pressure is denoted by this term P naught. Now, obviously, this derivation has been done for each kind of scenario, and it is quite possible that in most of the examples that you encounter, that this P naught will be equal to zero. So in the final expression for the stresses, maybe you have this kind of equation P naught P1 over radius, something like that, and plus Pi P naught. So, or so in that derivation, if you don't have any sort of external pressure, or there is no material that is present outside the cylinder, so you will obviously take this term P naught equal to 0 and solve the rest of the equation to get the stresses. So we have considered all sort of scenario for this type of cylinder and make a generalized equation. And then we have this radius r naught, which is the radius of the external thickness of the cylinder. And then we have this radius ri, which is the internal diameter or internal radius of this thick cylinder. And there is a significant difference between the internal and external radius, as we discussed, that this is the primary difference between a thick and a thin cylinder. Now let's assume that we take a differential element, which is this element which is shown in this black shaded region, and this differential element is located at a distance of radius r with respect to the center of this cylindrical element. Now if I show the magnified image of this cylinder or of this differential element, it will be something like this one. Now this over here is the top surface which is shown, which is this particular surface. And then this bottom surface is this one which is shown over here. And I have shown this figure in three dimension or 3D dimension, and I will just explain that what is the purpose of this one. Now you know that on this bottom surface, we will have radial stresses that will be acting, and this radial stress will obviously be opposite to this Pi, which is being exerted by the fluid that is present inside this cylindrical element. Now, this radial stress is obviously in 3D. If I see that radial stress will be acting on this particular face, which is this bottom face. And then since we have this P naught which is also acting on this cylindrical element, and this P naught will also produce some kind of radial stress which will be opposite to this direction of this P naught force. Now that radial stress is also denoted by sigma r, and since this particular radial stress is acting at a certain distance with respect, for example, if sigma r is acting on this internal surface, then obviously on this external surface, the stress will have a different magnitude, or there will be some maybe increase or decrease depending on the sign conventions or the direction of the external and internal pressure. So to represent that difference, we will say that this external radial stress will have some increase or decrease, and this increase or decrease is represented by this differential radial stress. So at the internal surface, we have this radial stress represented by sigma r, and at the external thickness, we will have some increase in radial stress, and that is represented by sigma r plus d sigma r. And if you remember, on the thickness of the element or on the stress that I have just shown, taken this image from the derivation of thin cylinders. Now, in that thin cylinder, we know that perpendicular to the thickness, we have another type of stress, which is known as hoop stresses. So, if I want to show the hoop stress in this figure, now since this is the cross section and this particular surface is the thickness of the cylinder, and in three dimension or in 3D, this surface is the thickness, or this is the thickness of the cylinder. So since these are a bit inclined surface, so perpendicular to this surface, we will have another stress, which is the move stress, and it is represented as sigma h, since it is acting perpendicular to this particular thickness. And since we have hoop stress on this right face, we will have another hoop stress on this left face, which is represented by sigma h, and these both are same in magnitude since it is acting on the same cross section of this rectangle, this cylindrical element. So this is about the stresses which are acting on different faces of this differential element. And just to represent that, if I take this distance, it will be from the center, and this distance which I have shown with a green line is equal to the radius of the cylindrical element. Now the same distance is shown over here from the center. Let's suppose this is the center of the circle, and from the center to the bottom surface the distance is this r, and from this bottom surface up to this top surface, which is this particular distance. Since we are taking a differential element, which is a very small element, so we will say that this particular distance is dr. And if I want to represent the total distance from the center to this top surface, it will be r plus dr. So this is the distance from the center to the top surface. So this is about the distances and the thickness. We have assumed that the thickness is also very small and we will take it as dx for now. Now the whole calculation that we will be doing is for the unit thickness. So anywhere or at any step when we will have this dx, we will assume it that it is the unit thickness and we will do the calculation based on that. Now, can anyone, one thing just I missed, that this angle over here is d theta, which is the angle between these two surfaces if we combine it with the radius. Now, since we have this angle d theta, can anyone tell me what will be this arc length? This particular arc. What will be this arc length?
Sir, R plus dr into d theta.
So this arc length will be not dr into d theta. We have to take the whole distance from the center. For example, if we have a circle, then this arc length will be this radius. If this arc length have radius into theta, but in this case, if I want to calculate this top arc length, that will be r plus dr into d theta. What will be this bottom arc length? This one.
Sir, R into d theta.
So this bottom, which I have shown over here as well. Okay, this arc length is r into d theta. Now, if we have this arc length, what will be this area or area of this particular surface? Can anyone tell?
Sir, 1 by 2 R square d theta.
Actually, this is a rectangular element now. We know that this length is r plus dr into d theta, and length this length which is going inside is equal to dx. So the area will be r plus dr into d theta into dx, right? Since we are doing this calculation for unit thickness, so we will take this dx equal to 1, and when I multiply it 1, then the area of this particular surface will come out to be r plus dr into d theta. And in the same way, if I
सर
calculate, yes,
ये तो कर्व है ना, तो कर्वनेस की वजह से इसका एरिया कुछ ज्यादा या कम नहीं होगा,
देखो
क्योंकि
हमने
ये
कर्व लेंथ निकाल ली ना, ये लेंथ हमें पता लग गई। अब ये लेंथ ज्यादा या कम हो वो उससे हमें लेना देना नहीं है, क्योंकि हमने तो ये लेंथ एंगल के अकॉर्डिंगली निकाली है, तो वो एंगल ऑलरेडी इसका इफेक्ट इनकॉर्पोरेट कर रहा है, राइट?
सही है सर,
So
सही
once
है
we have the length, हमें पता दूसरी length तो straight है, so that length is dx, so we will simply multiply it and to get the area. And in the same way, if I want to know what is the area of bottom surface, that will be r d theta into dx, and when I multiply it with 1, so the area will again be r d theta, and that area is shown over here, which is r d theta. Now,
सर, आप
these
dx को 1 क्यों, सॉरी सर, सर मैं पूछ रहा था कि आप dx को 1 क्यों एज्यूम कर रहे हैं?
we are doing this for the unit thickness, and later on we will include the element of thickness. We will see. Tisra, you might not have done the slab calculation. Actually, unit thickness का मतलब ये है कि आप थर्ड डायमेंशन को ना एक फॉर नाउ, क्योंकि थिकनेस जो है ना वो कांस्टेंट है सिलेंडर की, राइट? जितनी थिकनेस शुरू में आ गई है वो वही थिकनेस रहनी है। तो आप जो है ना स्ट्रेसेस और फोर्सेस इसीलिए टू डायमेंशन में कर लेते हो कि जी आप विद रिस्पेक्ट टू एरिया, अब स्ट्रेस क्या होती है? विद रिस्पेक्ट टू एरिया होती है, राइट? अब इसमें आपको वॉल्यूम का भी तो इम्पैक्ट लेना चाहिए, लेकिन वॉल्यूम या वॉल्यूम और आई कैन से थिकनेस का इम्पैक्ट, ठीक है, लेकिन वो स्ट्रेस को इसीलिए एरिया से शो किया होता है कि थर्ड डायमेंशन वैसे ही कांस्टेंट है, और अगर आप एरिया के अकॉर्डिंगली रिप्रेजेंट कर दो तो दैट इज आल्सो फाइन, राइट?
ओके सर।
So coming on to this one, if I want to represent what will be this area, we'll just erase this one. What will be this rectangular area?
dr into dx.
Sir, dr into
So
dx.
that will be dr into dx, and if I again simplify this one, that will turn out to be
dr.
dr. So now we know the areas on which all these stresses are acting. We know the area of this surface on which this sigma r plus d sigma r is acting. We know the area of this side surface on which this hoop stress is acting, and we also know the area of this bottom surface on which this sigma r is acting. So if I want to convert these stresses into forces, or if I want to make the force diagram, what will be that? Let's say stress is equal to force over area, and force will then be sigma into area. And if I want to show the force diagram, let's call this as a force diagram of this three-dimension shape. That will be something like this one. This is the front view. And on the top surface, if I multiply these two factors, sigma r plus d sigma r into r plus dr d theta, that will give me the force that is acting on this top surface in two dimension. And since we are working in two dimension, that is why we have one factor over here, which represent dx, or the thickness. And then on the bottom surface as well, I have multiplied this stress with the area of this surface, and this will be my force on the bottom surface. This angle is d theta, and on the right surface my stress was sigma h into, again the area is dr, and similarly on the left side again I will have the same stress, that is sigma h dr into 1. So this will be my stress on the left side. Now there is one thing that is shown over here, that is this angle d theta by 2. Now we know that this angle is d theta. Can anyone explain why this angle is d theta by 2? Take 30 seconds and try to figure out that why this angle is d theta by 2. Anyone can explain the correlation? Now we know that this hoop stress is acting perpendicular to this inclined surface, and this is the horizontal surface. If I this is the hoop stress, what will be this angle? This angle is obviously d theta by 2. What will be this angle now? Anyone?
So 90 minus d theta by 2.
This total angle is 90, and this angle will be 90 minus d theta by 2. Now if this angle is 90 minus d theta by 2, what will be this angle? The bottom one, which I have shown with a black line.
d theta by 2.
So this angle is 90, and this bottom angle, let's call this x, will be 90 minus 90 minus d theta by 2. And if I simplify this one, that will be plus d theta by 2. This will cancel out, and this x angle will be d theta by 2, which is the same angle which is shown over here. The angle of this hoop stress with the horizontal surface is d theta by 2. So this is why, or it is for this reason, that this angle is shown over here as d theta by 2. Uh, is this clear?
Yes, sir. Yes, sir.
So now coming on to, is my voice audible?
Yes, sir, ये 175 का mic on है, sir, I guess. You are audible, sir.
What?
Sir, आपकी आवाज़ आ रही है.
Okay. Let's now, if you have understand this figure, then the rest of derivation is quite simple. It's just simply the simplification of force equation or equilibrium equation. Now let's say if we take sigma Fy is equal to 0 for this force diagram. Now how many forces I have in the y direction? One force is this one, and that will be sigma r plus d sigma r into r plus dr into d theta dot 1. The other force is this downward direction, that is minus sigma r dot r d theta. Then we have the force or the y component of these two hoof stresses. If I represent the y component, one will be in this downward direction, and that will be sigma h dr, and that will be multiplied with the sine 2 theta by 2. And in the same way, the sine component of this sigma h will also be sigma h dr sine d theta by 2. And if I show this into this equation, these two are same, so they will simply add up, and we will have 2 sigma h dr sine 2 theta by 2, that is equal to 0. So we have this particular equation, and if I simplify this one briefly, I will get sigma r dot r plus sigma r dr plus d sigma r into r plus d sigma r into dr minus sigma r dot r minus sigma h dr d sigma r dot d r. Now this will be the equation that we are going to get. So over here I have ignored this d theta term because these angles are very small. Just give me a moment. There is so much disturbance behind me. I'll just go. I'm just going to check. I can't focus right now. Give me a moment. Okay, in this equation, wherever you might see the terms where you have the product of these two differential, for example, this d theta or dr, or this d theta into d sigma r, we will just ignore this term because obviously the sum will be quite small, and it is the sum of these differential will be quite small, and overall there won't be much impact on the results. due to these products. So if I further simplify this product, or if I further simplify this equation, these two terms will cancel out and I will be left with sigma r dr plus rd. Now since this angle is also very small, so the sine theta of this angle will obviously be almost equal to again equal to 1. So I think what is sine 0? Can anyone tell?
0 होगा सर.
सर जब एंगल स्मॉल होता है तो फिर साइन थीटा थीटा की इक्वल होता है सर.
Yes. So when we have this angle which is very small, so we are going to get this angle equals to theta. So let's keep it like that. So we have over here sigma r dr, then this term will be with us, that is d sigma r into r, and I can represent it as r d sigma r, and the third term that we will have is this. Obviously, we can ignore this term because again, this is a product of two differential terms. So we will be left with this final term. And over here, since we have the angle as sine d, I just have to represent it like this. We have this angle as sine d theta by 2, so it can be represented as d theta by 2. And if I represent it over here, this 2 will cancel out with this one, and I will be left with sigma h dr into d theta equals to 0. I think I have missed one point in this figure. Just give me a second, let me just recheck. I think I have missed something in this figure. Okay, actually there is something that they have ignored this angle. I missed maybe something, or I couldn't find a proper reason for this one, but I will definitely going to check this one. I will let you know in the next class that why we are ignoring this angle d theta, and probably the reason would be that maybe the value is very small. But again, I will check this in the literature about this reason and let you know. So for now, let's just not spend too much time on this one and continue with the derivation, and later I will explain it to you. So if I continue this with this one and divide this whole equation by dr, I will get sigma r over here. Then I will have plus r d sigma r over dr, and the last term that I will be left with will be sigma h equals to 0, or I can write it like this one. Now let's name this equation as our equation 1. Now initially we made some assumption, and one of the assumption was that the longitudinal strain will remain constant. And what is the purpose of that assumption? We will see it now. Now can anyone tell me how I can represent the longitudinal strain in terms of hoop strain and the radial strain. We did that in the last class as well for the thin cylinders. What is the way to represent the strain? Anyone? So if I want to represent the longitudinal strain, since we know that when a strain is acting in one particular direction, it tends to reduce the strains that are acting in the other two directions. So the total strain in the longitudinal direction will obviously be the longitudinal strain itself minus hoop strain, and it should be multiplied with the Poisson's ratio. And the third term that we have is the radial strain in this equation. And since it has been mentioned that this longitudinal strain is constant, so we will take it as a constant. And once, if I want to represent it in terms of stresses, that will be obviously be in terms of this modulus of elasticity, and I will get this equation for the longitudinal strain, which is termed as a constant. Now we know since the strain is also constant, so obviously the longitudinal stress will be a constant factor. And if I briefly simplify this particular equation, and the first assumption in this one was that the material properties also is material is also homogeneous and isotropic. Now that property states that these two factors, which are related to the material thickness or the dimensional or the cross-sectional dimension of the material, will also remain constant for a particular cylinder. Now if I briefly simplify this equation, I will have there is hoop stress plus radial stress equals to, there is a constant over here, let's call this as C, and if I take E onto this side, it will be something like this one, and then if I take this longitudinal stress onto this side, we will have sigma L over here, and this nu will be divided, and finally we will have a negative sign with this whole equation. Now we know that this stress is also constant, these are factors are also constant for a particular factor, and this person who is Gabriel Lamb called this constant as 2a. Now this a is called as Lame's constant, and if we have been provided with a particular cylindrical element, we know that these properties will remain constant for a particular cylinder. They won't vary with respect to the dimension or with respect to the location where we have cut section. So the purpose of this constant is to make or introduce some kind of convenience in the calculations that you will make, or the numerical problem that you are going to solve. So for example, you have been provided with a cylinder, you will first directly calculate this constant 2a, and then you will see that when we simplify further these equations, we can get the values of these two stresses quite conveniently. Let's call this equation as equation 2, and if I further simplify this one, it will be sigma h is equal to 2a minus sigma r. Now if I substitute this equation in our original equation 1, which was this one, now if I substitute the value of sigma h into this one, I will get this sort of equation, that is sigma r minus 2a plus sigma r plus d sigma r over dr. Now you can see that we have used the initial assumptions that we made before this calculation to derive the relation for the stresses or these strains later on. So from this equation, if I simplify this one, I will get d sigma r over dr dot r equals to 2 times a minus sigma r, and if I rearrange this one, I will get 2 into a minus sigma r equals to 2 times dr over r. I have just taken this r term or these two derivatives, or I have just kept these two derivatives together. Now, since we did this derivation, we are doing it for a differential element. If I want to separate it over the whole area, then I have to take the integral of this equation or integrate this equation. Once I do that, I am going to get a generalized equation for the whole cylindrical element. Now, if I integrate this equation, I am going to get this sort of form, that is 1 over 2 into A minus sigma r into d sigma r, and on the right side we have 2 over r into dr. Now can anyone tell me what will be the integral of this particular equation of the left side? Khizar,
Sir, 2ln 2ln r, sir.
what is that? Can you come again?
Sir, minus
The right side वाला पे
ln
2ln r.
ln sigma r divided by 2.
For the right side, we will have obviously 1 over r, that integral will be 2 ln or natural log into r plus constant, right? I
Yes,
believe
sir.
everyone
Yes, sir.
Yes,
understood
sir.
this one. And for the left
Yes,
side,
sir.
my integral would be log natural into a minus sigma r, and the third term will be obviously minus 1, and so this will be the integral for the uh, left side of this equation. Is it clear?
सर ये 2 रह गया आपसे सर, लेफ्ट हैंड साइड में डिवाइड नहीं होगा.
Okay, yeah. We have this 2 factor as well on this left side. So let's just keep it over here. Now, if I further simplify this equation, I'm going to get, obviously there is a negative sign with this one. So we will have minus log natural into a minus sigma r divided by 2, and on the right side I have 2 log natural into r. Now can I represent this natural log? Just give me a second. Okay, sorry for the delay. Actually, I think we made one uh, error over here. This 2 is not on this side because there was 1 2 in this term, which is this one. So I have kept it over here. So I represented it twice over here. So just make this correction that we will have only 1 2 term in this equation, right? So this 2 we have already taken on the right side. So over here, just remove this one and this 2 as well. So now let's simplify this one. Can I represent it something like this one? Because this is a property of log that if you have this product 2 on the right side, you can just take it on, keep it as a square of this variable term. And on the left side, let's keep it as it is, that is log natural a minus sigma r. Now, if I briefly simplify this one further, I will get log natural r square plus log natural a minus sigma r, and that will be equal to minus c. So I have taken this minus side on the right side and move these two terms together. Now again, if I apply the property of this natural logarithmic natural log, that means if we have the sum between the two logs, we can also write them as a product of these two terms. That will be a minus sigma r into r square, and this will be equal to minus c. Now if I want to remove this log natural, I have to take it into the exponent. So that will give me a minus sigma r into r square equal to exponential minus c. Now this exponent e minus c is represented as b, and this b is the second Lem's constant. So since this is also a constant value, so it is represented by this factor b. Now in most of the question, now first let me just finish this one, then I will explain the significance of these two constants. So that will give me a minus sigma r into r square is equal to b, and if I simplify this one, I will get a minus b over r square. Now this is one equation for the calculation of radial stresses, and if I substitute this one into our original equation 2, which is over here, if I substitute that equation into this one, I can get the value of hoop stress or the equation for hoop stress in terms of this a and b. So if I substitute it in 2, I will get this equation, that is sigma h is equal to 2a minus a plus b over r square, and that equation will be a plus b over r square, right? So this will be my equation for hoop stresses, and this one is my equation for the radial stresses. Now in both of these equations, there are two constants a and b. In most of the literature, you will find these as your final equation for the calculation of hoop stress and the radial stress, but it is not always the case. Because reason is that once you have these equations, you have to apply the boundary condition first to find out the values of these two constant a and b, and once you have the values, then you substitute into this equation to get the final answer. Obviously that procedure is also correct, and you will get an understanding that how you can apply the boundary condition once you solve these problems. But for now, or for this course, we are going to simplify these two equations so that we have one final equation, and we simply substitute that equation into our question or into our answer to get the final answer. Now, if I come back onto my original shape, and if I want to figure out the values of these two constant a and b in terms of radius, we have to come back into our original shape. Now, in this shape, if I want to write the boundary condition, I can say that at a radius of r is equal to ri, which is this particular radius, we have stress sigma r is equal to minus pi, which is this stress. So obviously the radial stress is of negative of this internal pressure. And then I can also write another boundary condition that at a radius of r is equal to r naught, we have again the radial stress that is equal to minus P naught, or opposite of this external pressure. Now these are my two boundary conditions, and if I substitute these boundary conditions into my equation number 3, which is or this equation, let's call this as third. If I substitute that those two boundary conditions into this equation, I'm just writing it over here. Now initially we wrote that at r is equal to ri, I know that the radial stress is equal to pi or minus pi, or r is equal to r naught, the radial stress is equal to minus p naught. Now if I substitute these two conditions into this one, I will get minus pi equals to a minus p. Now this r will be internal radius, and then the second equation will be minus p naught, which is due to this condition, and that will give me a minus b over r naught square. Now if I subtract these two equations, and my purpose is to get the values of A and B in terms of these internal pressure and radius. And the benefit for that will be that once I have this A and B in terms of these internal and external pressure, these are all known factors for a particular cylinder. So I will simply get one generalized equation for sigma R or sigma H. So first let's subtract this equation, and if I do that, I will get minus pi plus p naught equals to minus b over ri square plus b over r naught square. Now further simplification, if I take it the LCM as ri square into r naught square, that will give me r naught square b plus ri square into b. Now if I take minus as common over here, that will give me pi plus, sorry, minus p naught, and if I take minus as common from here as well, or minus b as common, I will get r naught square minus r I square divided by r I square into r naught square. This minus sign will cancel out, and for this constant b, I have one equation, that is ri square r naught square pi minus p naught over r naught square minus ri square. Now this is one equation for the constant b. Now we have represented this constant in terms of internal radius, external radius, pi, p naught, and the two radius again. So if I substitute this b in this equation, then I can get one equation, but since again we have one constant a over here as well, so we need to find the value of this a as well. So let's suppose I call this equation as equation 4, and if I substitute this b which I have calculated over here into this equation 5, then I am going to get the value of a. So from this equation, obviously a will be equal to b over ri. By the way, there is a square term over here. So a is equal to b over ri square minus p of I. So if I substitute the value of b which I have just calculated over there, so I will get r naught square pi minus p naught divided by r naught square minus ri square minus p of I. Now you can do the simplification. I'm just writing the final equation of A that I'm going to get using this particular, or by simplifying this one, and the final equation will be Ri square Pi minus R naught square P naught divided by R naught square minus Ri square. Now this is the equation for this constant A. Now I have both the equation of A and B. Now let's come back to our original slides. Uh, if I share with you the slides. Now in this slide, actually the whole derivation is given in this slides, and I have already uploaded it on CMS, so you can find that over there. So we have derived our equation for A and B just like these one. This is the equation for A and B, and this one is the equation for A, which is written right over here. And we also calculated these two equations in the derivation that we just did on our whiteboard for sigma r and sigma h. Now, if I substitute these two constant or these two factors a and b into these equations, I am going to get these particular equations for sigma r and sigma h. Now, in these two equations, you can see that sigma r is a function of internal radius, external radius, internal pressure, and the external pressure. And in the same way, sigma h is also the function of these two equations. Now, once you have these two equations, no matter what is the case, even if P naught is zero, if external radius is obviously external radius is not going to be zero. So whatever is the case, you can simply use these two equations to get the values of your radial stresses and the hoop stresses. So this is one generalized derivation for the calculation of these two stresses. And in the literature, you will also find two particular cases. One is the case, for example, let's assume that we have a cylindrical element in which we don't have any sort of internal pressure, right? So in that case, if I want to write down the equation for sigma h or sigma r, then again I have to understand that these two variables are going to change. These two Lame's constant, which are a and b. And how I'm going to change that? Obviously, in the case when we don't have any internal pressure, my boundary condition will be changed. So the boundary condition will be that uh, in this case, obviously, we only have the internal pressure and there is no external pressure. So initially, just like I told you, that in that case, we don't have the internal pressure and my boundary condition will be that at a radius r is equal to r internal, the pressure or the radial stress is equal to minus pi. And at r is equal to external radius, my radial stress is equal to 0. So these will be my two boundary conditions, and these two boundary conditions will then be substituted into the equation of sigma h and sigma r, which I have calculated over here to get the two A and B equation. Now these A and B equation are valid for this particular case only, that when we have a cylinder with internal pressure only. And once we have this equation for A and B, we can substitute into our original sigma H and sigma R equation to get the generalized expression. But again, these cases are valid if you directly want to use the A and B constant for this particular case. But that is fine if you use this equation. And in this equation, let's suppose if there is no external pressure, these terms will by default turn out to be 0, and it will give the same answer as we get from these two equations. And there is another case. Now, in this case, if we have only the external pressure, then in that case, in my boundary condition at R is equal to R internal, I can say that the radial stress is equal to 0, and at R is equal to R external, my radial stress will be minus P naught. So in that case, obviously, this factor will turn out to be 0, and the other factors will remain as it is, and those will be your generalized equation. So this is about the derivation of the radial stresses and the hoop stresses, and we have discussed two particular cases. Now we also have these equations for this case, but obviously you can use your generalized equation and that will also be fine. And obviously it is a bit long, but if you do it by yourself again, you will better understand, or you will see that it is not that much complicated. You simply have to move or simplify your initial force equation to get to this point. Any question about this one?
सर ये डिराइवेशन आ सकता है फाइनल एग्जाम में?
Yes.
एक्सक्यूज मी सर, ये फॉर्मूलाज गिवन होंगे पेपर में कि हमें याद करने होंगे?
These formula, I will suggest you to try to memorize this particular formula because it is quite obvious and quite common in most of the exams. You are going to encounter these kind of formula, so try to memorize this one. And this
Okay,
particular
sir.
if you remember this one formula, it is valid for all these three cases, right? So this is about the hoop stresses and radial stresses. For the longitudinal stress, actually the derivation is quite simple. It will just take 1 or 2 minutes to complete that one. So we know that the longitudinal stress is acting along the, if we cut the cross section, let's suppose this is a cylindrical element over here, and if I cut the cross section, as I explained in the case of thin cylinder as well, that the cross section perpendicular to the longitudinal stress, then we will longitudinal length, or the length of, perpendicular to the length of the cylinder, then we will have longitudinal stresses that are acting on the thickness of the cylinder. Now these longitudinal stresses are represented over here, and these two stresses are obviously due to the internal pressure, and these stresses are obviously due to the external pressure, which is written over here as P naught. Now, if we want to convert these internal pressure into forces, can anyone tell me how I can do that?
एरिया से मल्टीप्लाई करेंगे सर.
So, what will be the area for this internal pressure?
RI given है सर.
So this internal pressure, you can imagine that these are acting only on the internal radius or only on the inside. So since this is the internal radius which is shown over here, and the area, since this is a circular element, I am just showing the cross-sectional view. So the internal radius will be pi ri square, because this internal pressure is acting on the internal radius, and this external pressure is acting on the external radius, so that will be pi r naught square. So this will be the external radius or the total radius of the cylinder on which this P naught is acting. So for P naught, I will, if I convert this into force, I will get this particular equation, that is P naught into pi r naught square. And for the internal pressure, the radius or the force will be this one, that is pi into pi ri into square. So this will be my external force, or due to the force due to external pressure, and this will be the force due to the internal pressure. And in the same way, if I want to write down the force for this longitudinal stress, now this longitudinal stress is acting only on this particular radius. And if I want to know what is this radius, I know that the total radius is r naught, or the total area is pi r naught square. And if I subtract the internal radius from this total radius, I am going to get the area of this particular shape or this much thickness. So that area will be pi r naught square minus pi ri square. And if I take this pi term as common from this one, that will be this equation, or this will the area on which this longitudinal stress is acting, right? So if I multiply these two terms, I'm going to get this equation. Now if I further simplify this one, I am going to get P naught R naught square minus Pi Ri square, or this equation I'm going to get. Now initially I told you that this longitudinal stress is constant, and that constant is represented by this A factor, which was the Lame's constant. Now there was one equation of A that we wrote in terms of nu and E, and this is the equation in terms of R naught and Ri. This constant A will give me the same value as I am going to get using those material properties, or using these internal pressure and the external pressure. So you can use either of the equation depending on the case that you are solving. So maybe in some cases you won't be provided with this internal pressure or radius. Then you can use this particular equation of Poisson ratio or modulus of elasticity to get the value of this sigma L. And why I am saying always that this is a constant value. For example, in this equation, you can see that we have P naught Pi. These P naught and Pi will remain constant. If you have been provided with a thick cylinder, then these variables are not going to change. And similarly, this R naught and Ri are also constant values. These will be same for a particular cylinder. So that is why for one cylinder, this sigma L will remain constant. But if you see this equation for this hoop stress, this radial stress. Now in this radial stress, obviously this Pi and Ri are constant factor, but we also have one this which is R square. Now this R square is a variable factor. This R square will tend to change. For example, in the question, it will be asked this R, for example, it will be asked that give us the value of hoop stress at a radius of 10 centimeter. Then what will you do? For example, maybe 10 centimeter is somewhere over here. Obviously, these R naught and Ri are a constant factor, but this R is a variable factor. So this hoop stress, you should keep this in mind that hoop stress and the radial stress vary with respect to radius or thickness, because this is obviously moving along the thickness. So they tend to vary with respect to the thickness, but the longitudinal stress, there is no factor which will affect that longitudinal stress based on the thickness of the cylinder. So that is why initially there was one assumption that the longitudinal stress remain constant and the hoop and radius stress will vary with respect to the thickness. So this is it about the derivation of stresses. So I strongly encourage you to again go through this derivation, and once you go through this, because in all the questions that you are going to solve, you have to apply some of the concepts from the derivation itself. So as long if you don't understand the complete procedure, then it will be difficult to solve the examples related to this one. So in the next class, we will do the strains for thick cylinders and solve some examples related to this one. So now any question about this lecture?